Chemistry is the study of matter, its structure, properties, and transformations. And transformations is just a fancy way of saying changes. These transformations or changes involve changes in energy. What is matter? Matter is anything that has mass and occupies volume or space. What is not matter? Energy. For our class, there are 3 states of matter: solid, liquid, and gas. Solids have a definite volume and a definite shape. Liquids have a definite volume but change shape to fill their container. Gases have neither a definite volume nor a definite shape. So these 2 phases, solid and liquid, are called the condensed phases. And that simply means the atoms are next to each other. There's no space between them, not much space between them. So here we have solid matter, and in chemistry, because while we can see matter, if we start to think of matter on a particulate level, an atom or molecular level, we are not able to visualize that. And so we often will draw pictures in our mind to explain what we see. So here we have a representation of how one of these cubes of matter might look. Here we have a representation showing how some amount of this liquid might look. And these are similar in that there's very little space between one atom and another. There's very little space between one atom and another. So solid and liquid matter stick together. Solid sticks together in a way where the atoms are locked in a spot. Liquids stick together, but the atoms can slide past each other. But the reason they're the condensed phase, solids and liquids, is because the atoms are sticking together. For gaseous matter, there is a lot of space in between atoms. So in this illustration, I want to point out something that may not even seem apparent or meaningful at first. And that is that the size of one of these spheres, which represents an atom, is the same for the solid and the liquid and the gas. And because the color is the same, green, 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 the author or the illustrator might have been conveying the idea that they were made of the same kind of atom. I want to point out that the volume that the solid occupies or the liquid occupies doesn't fill the container, but the gas does. And the reason it does isn't necessarily because there's more gas atoms, it's because there's more space between them. So the size of an atom in liquid and that same kind of atom in a gas does not change, just the space between it increases. So back to solids. So for some solids, they have what we describe as a crystalline structure. And that just means that there is a 3-dimensional pattern that continues out in every direction. And regular refers to like the bond angles are all the same. It's always the same angles. So regular has to do with uniform. So here we have carbon in the form of a diamond, and there is a regular 3-dimensional repeating pattern. Here we have carbon in charcoal, and we would refer to the lack of pattern as amorphous or without shape. So this brings up an opportunity for one of those funny chemistry words, and that word is allotrope. So carbon in the form of diamond and carbon in the form of graphite are both carbon, the same element. They just exist in a different way. Some allotropes that we may be more familiar with would be allotropes of oxygen. So we're familiar with O2, which we refer to as oxygen. That's what we need to breathe. And then there is also a form of oxygen, a different allotrope called ozone. And ozone is necessary, it's just we don't want to breathe it. So O2 and O3 are both allotropes, and they're good allotropes of oxygen. It just depends where they are. Ozone in the stratosphere, protecting us from UV light, good form of oxygen. Ozone down on Earth, irritating our lungs, not where we want it. Okay, so we can classify matter according to, is it a solid, liquid, or gas, according to its phase, or we can classify matter in this way. We're going to look at, do I have one kind of thing? Or do I have more than one kind of thing? So pure simply means not a mixture. There's only one kind. And it might be only one kind of element or only one kind of compound. But there's only one kind. A mixture is a mix of more than, I'm going to say 2 or more. Things. And so we can have a mixture where things are well mixed and about the same size. We call that a homogeneous mixture. In chemistry, that's very important. Solutions are homogeneous mixtures. But more often, the mixture is not well mixed because things are different in size or different in density, and then we get a heterogeneous mixture. So we're going to look at how to classify matter. Is it only one kind of thing or several things? And if it is only one kind of thing, is it something I can find on the periodic table or something made from elements on the periodic table? So this is a chart that is in your book. And one of the things I love about Tro's products, the book we have for this class and the book I use of his for a different class, is that he's got great illustrations. And so as you're reading the text, be sure and slow down and look at the pictures and think about what is all the information being summarized. This picture has a lot of good information. And it's a flow chart. So I'm just going to walk through this flow chart with you. We're going to start with matter. What is chemistry? The study of matter, its structure, properties, and transformations. The matter can be just one kind of thing or more than one mixed together. If it is just one kind of thing, can I find it on the periodic table? Or is it made from things on the periodic table? And if it's a mixture, if there's more than one kind of thing, is it well mixed? Or is it not well mixed for reasons? Okay, so starting with pure. As you read the textbook, you're going to run into some sentences that are a little daunting. At first, they are confusing, and that's normal, and that is not a statement about you. That's just a statement about the subject. So you might run into a sentence like this. What is a pure thing? So here's a definition. It's a single kind of, it's a single kind of matter that cannot be separated into other kinds of matter by any physical means. Huh? Okay, so that's a lot of words. When you read a sentence like that, slow down and think about it. Let me break this down. A single kind of matter, well, everything that isn't energy is matter. So one kind of stuff that cannot be separated, Okay, separated I think means pulled apart into other kinds of stuff by physical means. So probably that still hasn't really cleared it up for you. And then there'll be an illustration nearby that's talking about that. And this is an example of one of those illustrations. So here, and sometimes it helps to have contrast. Pure means not a mixture. So here we have a mixture, and I can tell it's a mixture because I can see there's something yellow in here, and then there's these little flecks of something dark. So I know that there's more than one kind of thing. That makes it a mixture. And then we see that we have a magnet. What does a magnet act on? Things that are ferromagnetic, like maybe iron. So maybe here I have sand and iron. Or you're not familiar maybe with the periodic table and the elements yet, but this could be sulfur and iron. But the point is, there's more than one kind of thing. We definitely have a mixture. And the function of the magnet is to separate the iron out. That's a physical separation. So that mixture, by contrast, is not pure. How do I know that? Because it is being separated. And the physical means here is that a magnet is acting on a property of iron, which is that it's ferromagnetic. Here's another example of not pure. So I'm looking at this thinking, ew, muddy water, definitely a mixture. There's more than one thing there. And the illustration tells us that this is a heterogeneous mixture of soil and water. When the mixture is poured through the filter paper, the larger soil particles are trapped and the water passes through. The water passing through the filter is more pure than it was in the mixture. So this is another example of a physical means, a way of separating physically a mixture into things that would be more pure. So an element is a single kind of matter that cannot be separated into other kinds of matter by physical means. Another question we might ask as we're working our way through this sentence is, well, if it wasn't a physical means, what kind of means would it be? And means here just means way. If it isn't done in a physical way, what other kind of way could it be done in? And the answer is chemical. So a sentence like this is a chunk. It's a mouthful, and it takes time to chew on that and digest what it means. But I just want to encourage you that it is worth spending time thinking about these words because you're building the muscle of reading material that is very precise, and it'll make you a stronger student in chemistry and in other classes. Okay. So now, pure means it can't be pulled apart into different kinds of things. And one kind of pure is elements. So right now, I would be, in my mind, flipping back to the chart that said matter can either be pure or a mixture. And there's two kinds of pure. One is elements, and the other is compounds. Okay, so we talked about matter can be pure. Pure can't be separated by a physical means. One kind of pure is elements. And then here's another one of those chunky sentences. A substance which cannot be decomposed into simpler substances by chemical or physical means. Okay, so at this point you're probably tired. Let me give you a shortcut. It's simply one kind of atom. An element is something that you can find on the periodic table. Can you find iron on the periodic table? Yes. I know the symbol for iron is Fe, and there it is. Can you find steel on the periodic table? No, steel isn't an element. That's why it's not on the periodic table. Okay, so here we have some different representations, and this is a thing that happens in chemistry quite a bit too. Because the nature of what we're looking at is tangible, I can see a puddle of mercury, but I can't see the atoms that comprise the mercury. Many times we'll have a representation of something that is what we observe, and then there'll be a picture that the author is trying to get us to form in our head about what that might look like on a particular level. So we have the actual, we have a mental picture, and then we also have words and symbols to represent those words. So here we have a few elements: mercury, sulfur. We're going to learn that sulfur has different allotropes, and the one that's common to us is S8. That is why the author has shown us a picture to put in our heads that has 1, 2, 3, 4, 5, 6, 7, 8 sulfurs all stuck together in a ring, because that's the allotrope that we'll refer to most often. Here we have copper wire, iron chips, and aluminum. So as you're looking at things like this, the goal of a picture like this is to tie in something that you've seen in real life. Maybe you've seen a spool of copper wire, to a mental picture, and to a symbol that we'll use on the periodic table. For this particular graphic, there's extra meaning in there that later, if we go back and look again, we might see, in a few slides we'll talk about different allotropes and how S8 is the sulfur that we are familiar with. You'll start to realize, oh, that picture actually was important. There's a reason that this looks different than these. Also, you'll notice as we continue to talk about in the Zoom lesson on the same subject, that there's other words in here like wire and chips. I can find iron on the periodic table. The word chips is just telling me something about the form that I might see it in my real life. And here we have aluminum solid, but the aluminum solid there looks like foil. So there's a lot of the pictures, and it's important to slow down and to go back and look at them again, to spend time in the book. Okay, so elements. An element can be recognized by a universally recognized 1 or 2 letter symbol. Usually, it's the first and the second letter, the first letter, or the first and the second letter. Sometimes, like for chlorine, it's the first and the third letter. The first letter is always capitalized, and the second letter is lowercase if there is a second letter. Okay, so there are some elements that exist in pairs, and we call those diatomic elements, and here they are. Starting at number 7 with nitrogen. And if we remember that hydrogen is a nonmetal, and it really does have a place over here on the periodic table. So starting with number 7, there are 7 elements. 1, 2, 3, 4, 5, 6, 7 that exist in pairs. There are 7. Di means 2, atomic, 2 atoms, elements. The 7 starting at 7. So we can see here bromine as a solid, and then the author wants us to focus on this spot and imagine the atoms lined up this way. Bromine, 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 lined up in a regular, repeating, 3-dimensional structure. We would call that a crystalline structure. So it looks like we just have bromine atoms lined up. But if we heat the bromine and the solid melts and becomes a liquid, and we focus on that, the author wants us to imagine here's 2 bromine atoms stuck together in a molecule near another pair of bromine atoms stuck together in a molecule, and another. So the smallest unit really is a pair. If we, of bromine atoms stuck together in a molecule, if you focus on the gas, we can see that bromine is a diatomic element. Each smallest unit is 2 bromine atoms stuck together. So this element is molecular, and its formula is Br2. To remember these, there's some mnemonic devices. So here's one. Horses need oats for clear brown eyes. Or many college students prefer this one. Have no fear of ice cold beer. So some elements are diatomic. Some elements are polyatomic. So poly just means many atoms. But it isn't like just a clump of atoms stick together. There is a pattern to it. So here we have phosphorus. Phosphorus, the common allotrope, the form we find phosphorus in, one form is called P4. So there's 3 kinds of phosphorus: white phosphorus, yellow phosphorus, and red phosphorus. P4 is the one that we use in our class. And then sulfur and selenium exist in groups of 8. We don't worry much about selenium, but in our class, there's going to be 3 elements that are polyatomic that we need to be familiar with. A student of mine gave me a mnemonic device to remember this, and I love it. Poor old Superman. He said it, and I just looked at him like, I don't know what you're talking about. And then he showed me phosphorus starts with a P. The symbol is P. And look, there's 1, 2, 3, 4 letters in poor. Old. Oops. 1, 2, 3 starts with an O. Ozone has 3 oxygens. And then Superman, guess how many letters that one has? 1, 2, 3, 4, 5, 6, 7, 8. So these are allotropes of polyatomic elements. They're molecules because there's more than one atom present, but they're elements because there's only one kind of atom present that you'll need to know in our class and the next. Okay, a compound is made from elements, and here's a definition. A compound is a substance which is characterized by constant composition and that can be chemically broken down into its elements. So it's something made from elements, but it's larger than just the elements. And constant composition has to do with the number of each kind of atom in the basic unit. Or it's simply something made of 2 or more kinds of atoms. Using symbols, the kinds and numbers of each kind of elements are combined to give chemical formulas. For example, sodium chloride is a compound, and we know the formula represents a compound rather than an element because there are 2 capital letters, which means 2 elements must be present. And because they're written next to each other, we know that they are chemically combined to form a compound. So are these elements or compounds? The first one is an element. How do you know that? 1 capital letter, and it's on a list you've memorized. Sodium. The second one is a compound. I know it's a compound because there's 2 capitals. How about that third one? O2. There's more than 1 atom, but there's only 1 capital, so this is also an element. And this element is a diatomic element. There's 2 atoms in a molecule. So this 2 makes it a molecule, but only having 1 capital makes it an element. Okay, here we have hydrogen, sulfur, and oxygen. 2 hydrogens, 1 sulfur, 4 oxygens, all combined together, that's a compound. 5 and 6 look very similar. 5 is an element, one capital, that's cobalt. 6 is a compound, carbon monoxide. So it is really important that you make it clear if the second letter is capital or not. Chemical formulas are a shorthand way to represent elements or compounds. Instead of writing out each element's name, we use its symbol. The number written subscript and to the right of the elemental symbol tells you how many of that kind. So one of our compounds there was this one, which is sulfuric acid. The number written subscript and to the right tells you how many of that kind of element. 4 is to the right of oxygen. There's 4 oxygens. The lack of a number here implies a 1. There's 1 sulfur. So, for example, water is written H2O. There are 2 hydrogens and 1 oxygen. So there are 3 atoms in every molecule of water. But if I know that there's more than just water in there, so we're told it's a solution of salt and water, the model shows that the salt and water consists of separate electrically charged particles, negative and positive, surrounded by water. So the particles cannot be seen. We can't, even with a microscope, see that there's particles in there. So if it looks like one thing, but you know that there's more than one thing present, that's a homogeneous mixture. Homo referring to same throughout. Homogeneous mixtures have uniform composition. Because the atoms and compounds that compose them mix uniformly. Examples would include things like air and Kool-Aid. So air is a mixture. And air has mostly nitrogen in it, some oxygen, about 21%. The third most abundant element, element, but the first most abundant species, which could be an element or a compound, is argon. And then carbon dioxide and all the other elements make up less than 1%. So air is a good example of a mixture. We know that it has more than one thing in it, but it looks like one thing. Kool-Aid is a great example to illustrate this idea of uniform composition throughout. So if I had a pitcher of Kool-Aid, it's possible that if I was to take a sample from here and here, if it was well mixed, it would look like one thing. It looks like a pink liquid. And a sample here would have the same composition as a sample there. And what that means is it would be the same intensity of pink. It would have the same sweetness. It would have the same, if we were to do some measurements, we could determine that the density was the same. So that is what's meant by uniform composition throughout. I can take a sample from anywhere and I'm going to get the same ratio of sugar to red dye number 4 to water. In a heterogeneous mixture, we have a non-uniform composition. And often we can see that. Not always, but often we can see that. The composition varies from one region to another. So an example of that could be something like where you can see it's non-uniform in the previous examples, or it could be something where it sort of looks uniform. But when they send you home with paint, don't they also send you home with a paint stick? And then if you don't, they put the paint on a mixer for like 15 minutes to shake it up. And then when you get home, you take that paint stick and you stir it a little bit because you want to make sure that you have the same composition. If you let the paint settle, you end up with thin paint up here and then thicker paint down there, sludgy paint. So if you have to mix it, that means that the density here and there weren't the same. Another example would be something like erythromycin, that pink medicine that you give kids when they have an ear infection. And you have to shake it up before you pour it out because it settles. So a heterogeneous mixture does not have the same composition throughout. Okay, chemistry is the study of matter. We can have one kind of matter, pure, or we can have more than one kind, making a mixture. The pure can be something we find on a periodic table or made from things we find on a periodic table. So here, the illustrator is showing us, look, there's only, one kind of atom here. And then here they're showing us there's more than one kind of atom, but it's always one of these gray in the centers and two of the reds on the outside. So that molecule and this molecule and this molecule, they're all the same. So that might be something like carbon dioxide, CO2. And this could be any element. I'll pick a gas that's monatomic, like argon. Okay, a homogeneous mixture. They're showing us in a small sample that we have two different kinds of things. But if I took a sample here and I took a sample somewhere else, I'd probably still end up with 4 of these orange monatomic atoms and 4 of these green diatomic atoms. A heterogeneous mixture is a mixture because there's more than one kind of thing, but they're not mixed well. They're in separate regions. Okay, that's your introduction to 2 ways of classifying matter. One is according to phase. Is it a solid, liquid, or a gas? And the other is according to composition. Do I have one thing or several things? Thank you for your time.